A retail network contains thousands of checkout registers. When they all attempt to push transaction data directly to a central database at once, the concurrent connections overwhelm the server, causing a system-wide collapse. Tying point-of-service business logic directly to physical database topologies prevents scaling. This creates a rigid architecture that breaks under the pressure of high-volume retail traffic. Oracle Retail Xstore manages this complexity using the Data Transfer for Xstore framework, or DTX. It acts as an invisible boundary layer between the register and the server. DTX serves as a dedicated data broker, isolating the POS application from physical backend data sources. This abstraction allows Xstore to operate against unified data models in memory, while DTX handles the specific details of connecting to JDBC or REST endpoints. It achieves this without the overhead of runtime reflection. Instead, DTX uses a deterministic, precompiled pipeline driven by XML and Java configurations. To understand the mechanism, we must map the data definition files, analyze the 6-tier compiler, and trace the routing queues. By separating business logic from database topology, DTX provides the architectural flexibility to customize retail environments without breaking the base application code. The foundation of this architecture begins with the .dtx file. This XML schema defines the data access objects. Every object requires specific attributes. The table attribute points to the database target, the package sets the namespace, and the extensible flag determines if custom endpoints can be exposed. Inside the DAO, individual field elements map specific properties of the object to exact database columns, assigning data types and primary keys. One specific parameter handles highly concurrent environments, the increment field attribute. If multiple registers update a single store bank session at the same time, standard SQL overwrites can lead to inaccurate totals. With increment field set to true, DTX calculates the delta between the old and new values and applies it at the SQL level, safely aggregating all concurrent register activity. Beyond individual fields, DTX maps relational data. One and one-many configurations link a parent object's properties to a child's targets. Many relationships require an intermediary cross-reference table, which the framework manages using the xref field attribute to map the mapping table to the child. Hydrating these complex relational trees introduces the risk of circular loading loops, where a child calls a parent that in turn calls the child. DTX prevents this using inverse relationships. This allows a child object to reference its parent without triggering the framework to automatically load or persist that parent. While the .dtx file handles the declarative schema, custom logic is placed in the .dtj, the data transfer for Java file. Developers can inject logic into the data model using a specific compiler tag, override generated method. When the compiler detects this comment, it renames the auto-generated base method by appending the word imp. This forces the application to route calls through the custom logic first. By separating declarative schema mapping from custom Java logic, DTX ensures the base architecture remains stable while accommodating local modifications. At runtime, raw configuration files are not used directly. They must first be processed by the DAOGen compiler. Triggered during the build phase, DAOGen processes the configurations and outputs a standardized 6-tier Java class structure inside the DTV DTX jar file. Layer 1 is the object ID class. It encapsulates primary keys and auto-generates the hash code and string identifiers to track objects in memory. Layer 2 is the model interface, representing the structural contract that declares all method signatures for the generated entity. Layer 3 is the DBA class. This isolates raw SQL commands like select and insert from the rest of the application. Layer 4 is the DAO class, providing the direct memory reflection of the database schema with getter and setter mappings for every field. Layer 5 is the model class. The Xstore application interacts directly with this layer, which houses custom Java logic and the eventer registry. The model class stores no values itself. It acts as a proxy, delegating all property calls down to the DAO class. Finally, Layer 6 is the relationship class. It houses the dedicated select queries required to hydrate an object's children. 2 overhead managers, Data Model Factory impl and JDBC Adapter Map impl, manage the memory instantiation and bind the correct adapters to these objects. The DAOGen compiler establishes a fixed class structure at build time. This ensures database interactions are strictly scoped and predictable before the application ever boots. Once the Xstore application manipulates these memory objects, the data must be routed back to physical storage. The data factory class is the gatekeeper for this process. Every data manipulation, access, and persistence event flows through its methods. Routing relies on sequence configurations. PM-type mapping config assigns the data model to a persistence manager type. Next, persistence manager config links that PM type to a logical routing strategy. Finally, data source config resolves that target into literal connection details, establishing the JDBC or REST pathways. Once the data is persisted locally, it is evaluated by the replication engine for distribution to central corporate servers. Retail networks are often unstable. Connectivity between a store and its headquarters can be severed unexpectedly. To ensure delivery, DTX utilizes a relegation strategy. When a transmission fails, the system tracks the failure count and exponentially delays subsequent retry attempts. This prevents the system from flooding an unstable network with requests. When full object hydration is unnecessary, DTX uses query config. This filters data into lightweight wrapped objects to optimize network reads. By abstracting the physical target into XML layers, DTX allows applications to persist locally and replicate to the cloud without changing underlying code. The DTX lifecycle operates in 3 distinct phases: definition, generation, and deployment. During definition, .dtx and .dtj files map schemas and inject custom logic cleanly alongside the base code. In the generation phase, the DAOGen compiler synthesizes these configurations into the standardized 6-tier architecture for every data entity. In the deployment phase, the data factory and relegation queues provide fault-tolerant persistence across distributed networks. Legacy retail software often relies on ad hoc database queries embedded directly in application code, making updates difficult to manage. The DTX framework systematically decouples business logic from storage topology. It maintains data integrity and provides an extensible architecture that accommodates complex distributed retail networks.